Thank you for joining us on this session for utilizing containers in games. My name is Daniel Whitehead. I am a senior solutions architect. I am joined here by Juho. Do you want to give yourself a quick introduction?
Sure. So I'm Juho Jantonen. I'm a specialist solutions architect for game tech.
So we're going to be looking at specifically containers in games and looking at how you can utilize them and why to utilize them while you're building out your game or your game backend services. As we're moving forward, we're going to jump into a quick introduction into games tech.
Yeah. So as you know, behind every great game, there's game tech, and AWS has the broadest set of services to bring any game to life, and also the most depth of features within those services. So we have a bunch of services specifically for games industry. For example, GameLift, which is designed to host game sessions, but also our full set of services, including compute, database, storage, analytics, machine learning, and so forth. We also have a global infrastructure of 22 regions across the world, spanning across 66 availability zones to build your services close to your players. And our infrastructure is trusted by some of the biggest game companies in the world and also some of the biggest games in the world, such as Fortnite, with hundreds of millions of players globally.
So as we're going through this session, we're going to be looking at a number of things. So first, we're going to start off with what are containers. We're then going to be looking at containers use cases in games, and then what are the container services that I can utilize on AWS. And while we're looking at that, how do I choose between which container service to be able to implement what I need to on AWS? And then we're going to close up with example use cases on a backend microservice, as well as game servers for specific implementation and guidance on how to utilize these within your game. So we're going to start off with what are containers. And to do that, we're going to jump right into what Docker is. So Docker is an open source project that allows you to build a lightweight platform on top of an operating system to create containers and automate the deployment of those containers onto that host. The process begins with a Dockerfile, in which it's a text file that is going to have instructions from the top to bottom that has all the dependencies and code to recreate a container and in a manner that allows you to take your code from dev all the way to production, repeating the same instructions on each one of those layers. So when we're designing a container, we're looking at containers to be able to help us with reproducibility, replication, and scalability, so that doesn't matter what the underlying host is, the container itself is going to have all it needs to be able to be operating and run on that host. We then move into what a container image is. So again, we have our Dockerfile, which is a set of instructions that, when it's read, is going to create images that are going to build on top of each other. So these images are going to initially pull from a base image, which you can see at the bottom here where we have Ubuntu. So that's going to be a base image. On top of that, we can actually build software by either pulling in or running commands in the Dockerfile to be able to build up until where we need to be. And on that top layer, we have our container that has a single read-write layer. Everything below that is a read-only, but on that top level, we have a single read-write layer that the container is operating in to be able to interact with either itself or the application or other containers as necessary. So Docker uses images within directories to build these layers, and they are reusable for multiple processes. So the idea is, once I have pulled all of the images, I can create one container, I can create multiple containers using those same dependencies and allowing myself to either scale that process out, but also making sure that I'm using the most of the underlying compute resources so that I don't have to keep pulling in dependencies that are going to be similar across multiple containers. So again, this technology is there to be able to help us cost optimize and utilize the underlying resources of our compute choice as much as possible. So we're going to be jumping into what the anatomy of a Dockerfile looks like. So we can see that this is a quick view of what of the example on the previous slide, where we have at that top layer, we're pulling our base image from a public image repository. In this case, it's going to be the Ubuntu image. And on top of that, we're then going to be running a run command. So this is going to be a shell command. I can also run as an executable to be able to do this. However, in this layer, I am adding all of the software that is going to be needed to be installed for this container in that single line. So this creates a single layer and installs all of this software. We then move down to the volume command, which this makes a location in that container that has a specific directory in which that container can either put data or share data with other containers to be able to have a place to have storage. The copy command is going to be a way for me on, let's say, my local test machine or on my build server to be able to copy a specific configuration into a directory. So in this case, I'm copying nginx.conf into the nginx directory in Etsy. So this allows me to take, a file that I've been working on locally to be able to then have that run within my container and have that be how my container is configured. We then have the workdir command, which this is an instruction that tells the container where we are in reference to where we're operating in reference to I want to run the commands on here. So in this case, the home of this container is going to be nginx, and then the next command after that is going to run the nginx application. And the final thing that happens within this Dockerfile is that we're going to be exposing the ports on port 80 and port 443. So this allows the container to be able to be listening on these specific ports to be able to have traffic coming in and then traffic coming out as necessary. As we're building these images, we have the ability to actually store these images in a repository. So again, I can source control my Dockerfile, and you absolutely should. This allows me to have iterable versions on top of that. But I can also do the same on the images that I need to be able to run my containers. So we have a couple of options in terms of having a repository where we can have these sitting in there. So Docker Hub is going to be a place where I can pull public images and provides private image storage that I can leverage. We also have Amazon ECR, which is a fully managed repository that is baked directly in with identity and access management that allows me to be able to have private repos that I can use identity and access management to allow access to and deny access to. So both of these are going to be ways that you can share your images with other team members. So if you need to be able to, you're working on one service, but you need to have somebody else take a look at it, having an image repository allows you to be able to have a scalable mechanism to be able to have that cross-sharing across your teams. One final note on an image registry is that ECR itself has a feature to be able to do image scanning on a container image. So the idea being, when I do a Docker a push into this image registry, I'm going to have something look at all the dependencies that are built into that image and going to tell me whether or not I have any compromised dependencies. So again, being a game developer, you're going to want to make sure that you can leverage security where you can, so that nobody necessarily has the ability to interact or break your game. So this is going to be one of the capabilities in terms of a security protocol that you can leverage by using a registry such as Amazon ECR. There are partners out there that you can integrate with and that do similar things, and those are going to be something that if you're not looking at Amazon ECR, you're going to have the ability to choose between those as well.
All right, so moving on to some key use cases for containers in games. So maybe the main one that we see is game servers. So game servers are basically stateful servers that manage your game sessions, and they are typically publicly accessible through a public IP, and your game clients connect over TCP and UDP. And you can leverage all of our container services, so including ECS, EKS, and Fargate that we'll be covering shortly to host your game servers. And one of the key benefits of this is that you can actually run the exact same server locally and test the features locally, and then deploy the same container image as a running container on your test and production environments. Another key use case is backend microservices. So what we mean by backend services, it includes things like player data management, leaderboards, matchmaking, guilds, chat, this type of functionality. And containers are specifically good for microservices because your microservices are typically small, and you want to be able to run a lot of these within a single virtual machine or an EC2 instance, and this is what you can leverage containers for. And typically, your microservices will be hosted behind an application load balancer or an Amazon API gateway, and we will actually come back to both of these use cases further down the session.
So this brings us to the container landscape within AWS. So we talked about the underlying container technology and its implementation on a single host, and we are going to be moving on to the number of ways to be able to run containers on AWS. In AWS, we have a number of options in terms of orchestration at that management layer, as well as hosting to be able to leverage to run containers the way with the responsibilities that you want to have for your game or your game backend. So we're going to start off with the management layer, and we're going to start off with orchestration. So Amazon Elastic Container Service, or ECS, or Amazon Elastic Container Service for Kubernetes, or EKS, are going to be orchestration layers that allow you to manage the lifecycle of your container operations. They're going to be provisioning the deployment of containers on a single host or a group of hosts, and ensuring the redundancy and availability of those containers on the hosts that you have those deployed onto. Another responsibility of the orchestration layer is going to be scaling up or down containers to reallocate load to ensure you're most effectively utilizing the underlying compute resources. And then if there are any problems with those underlying containers, we are going to, the orchestration layer is going to be able to detect that there's an issue and gracefully, hopefully gracefully terminate the problem, and then spin up new containers to be able to replace them. Moving down, we have two options for hosting. So we either have going to be Elastic Cloud Compute, in which this is going to be a choice for you if you want to be able to manage more of your infrastructure, or we're going to be looking at AWS Fargate, which is going to be a serverless approach to be able to run in containers. And then last but not least, as we talked before, we have the container image registry to be able to store and make sure that your images are going to have the security and control that you want around them. So jumping into this, we're going to be talking about Amazon ECS, which is going to be a fully managed container orchestration platform that operationalizes your container workload at a very high scale and a multi-tenant service that can spin up a large number of clusters and services and tasks underneath that. So as I just mentioned, clusters, tasks, and services, we're going to be jumping into what these constructs are. So the first thing we're going to be talking about is going to be a task definition. So a task definition is going to be analogous to essentially a Docker image. This acts as a base or a definition of what the container is going to be running within ECS. So we're going to be having an image URL that is going to be pulled down for that. We're going to be allocating specific resources on how much compute resources we want to be able to allocate to that container. And we're going to be having networking and other kind of configurations where if we need to have implementations of that container, it's going to be able to work the way that we expect it. Moving over to a task, this is going to be a class instantiation of that task definition, right? So I can have one to many tasks associated with a class definition that's going to allow me to increase that across a underlying host. We then move to a service, which is going to be one or more underlying tasks that are bundled together to achieve some purpose. So in this case, I might have an authorization workload where I need to have four or so containers that or tasks working together to be able to operate on a single interaction with my game client. Those would be considered a service together. So when I have a service, I can put them behind a load balancer that allows me to scale these across, to scale up and down based upon need, but I can also detect whether or not the underlying tasks of a service are healthy or not, to be able to remove them if they are unhealthy, and then spin new ones up to be able to ensure that they are healthy. Metrics can be gathered at the service level to be able to see, what the amount of load and the services is going to be. We then move to a cluster, which is going to be a collection of EC2s that are the underlying compute resources that are being utilized by ECS to place containers inside and scale them across the available compute resources for the cluster. Each EC2 can ship logs from the container over to Amazon CloudWatch Logs for debugging, as well as metrics can be seen at the host level. So similar to the Dockerfile implementation, this is going to be a task definition anatomy. And you can see at the top, we have the family, which is going to be the family of tasks. It's kind of a nomenclature for how you want to name your tasks. We then have the networking mode, and then you can see the container definition, which is going to look very analogous to essentially a Dockerfile. And you can see that there's a lot of things that map almost very similarly to that. And on the bottom, we have two parameters that allow us to be able to dictate how much of the compute resources that I want to grant to this specific task. This brings us to Amazon ECS and the ability to have different kinds of deployment strategies for the underlying containers to run on the EC2s that we have in our cluster. So in this example, we have 3 availability zones, and we have a number of containers, instances that are running on there, and containers that are running on top of those instances that are all talking to the ECS control plane. When they're talking, when the ECS placement engine is looking for a place to be able to put a new container, you have a number of knobs and controls that you have access to be able to tell it what you want it to do. So the first one is going to be a random deployment strategy, in which it's going to pick a place where it can run a container at random on the underlying resources that you have. The next option that you're going to have is going to be spread, which this is going to allow you to place tasks evenly based upon a value across the underlying resources. So I might not necessarily want to have it randomly placed across everything. I might want to be able to have a single container running on each of my underlying hosts to make sure that I don't have a single point of failure on my underlying container hosts. The third option that you have is going to be bin packing. So this is going to place tasks based upon the least available amount of CPU and memory. And the reason why this is powerful is that this is a cost savings effort that it's going to be finding places where the container can run with and maximizing the underlying compute resources of your cluster. With that, you have the ability to integrate Amazon EC2 spot instances into ECS. So when you're combining spot instances, which you can get at about 90%, up to 90% discount, combined with bin packing, which is going to find the best cost optimized way for running your containers on that infrastructure, you're going to find a very powerful cost optimization strategy within this paradigm. This brings us to Amazon ECS and looking at the underlying EC2 instances that you're going to be bringing into your cluster. There are a number of things that you need to have as prerequisites to be able to run an EC2 as a cluster, as part of your cluster, and that's going to be the Docker agent as well as ECS agent. However, before we jump into that, we have an ECS AMI or Amazon Machine Image that allows us to be able to have it's pre-built with the recommendations from AWS to be able to get an AMI or an EC2 into a cluster as quick as possible. Now, you can build your own, but to be able to build your own, you're going to need to have the Amazon ECS agent as well as the Docker agent on top of those EC2 instances. And just to mention, as with the Dockerfile or the Docker is an open source project, the ECS agent itself is open source as well. This then brings us to the other orchestration agent that you have, or the other orchestration engine that you have access to within AWS, and that's going to be Kubernetes. So Kubernetes is a rapidly moving open source project with a lot of enthusiasm around it. It's a platform for running microservices at scale, and Kubernetes can run anywhere. So we're going to be taking a look at how AWS has implemented the control plane of Kubernetes in a highly available manner, allowing you to be able to leverage a managed endpoint and introduce worker nodes into that, so that you can utilize that managed the managed endpoint and run pods. So pods are analogous to tasks in ECS. Run pods on these worker nodes to be able to scale up and down your cluster. EKS has similar to ECS, an EKS optimized EMI that you can leverage to be able to spin up these worker nodes quickly and have them effectively be ready as quick as possible. On top of that, you have 3 different types of autoscalers that are going to be built into EKS that are on GitHub. The first is going to be the cluster autoscaler that's going to adjust the cluster size due to lack or underutilization of resources. We're then going to have the horizontal pod autoscaler, which is going to scale up or down the amount of pods within a EKS cluster, as well as the vertical pod autoscaler, which is going to automatically adjust the CPU and memory reservations for those pods that are running. Similar to what we did with the task definition, this is an example of a pod configuration for EKS, in which you can see from everything on the template side down, it's going to look very analogous to what we've already taken a look at prior. Now that we've done a primer on the orchestration engines that you have access to in AWS, we've seen customers adopting and managing complex containerized applications. However, we still see that customers are required to manage more than just their containers. So specifically, we're looking at the underlying EC2s for both the worker nodes as well as the cluster instances, and you're required to be able to patch and maintain the OS. You have to keep the agents up to date. There's more things than you might necessarily want to be able to have to worry about than just running your game and running your container. This is one of the reasons why we built Amazon Fargate. So the idea here is that there's not 2 levels of management scale anymore. Specifically, what you should think about with Amazon Fargate is that I have a service, I need to define what metrics I care about, and then how many of these services that I want to be able to run. Everything else, Fargate is going to be able to leverage. You also have the ability to run Fargate as both an ECS as well as EKS target. So this is going to be something that's going to then take off the underlying instance maintenance of the EC2s and make it so that you can focus specifically on either your game's backend or your backend game servers.
Okay, so if we recap on the different orchestration options, so actually on the bottom here you can see EC2. So actually instead of using ECS or EKS for your control plane, you could build your own and run it on virtual machines on EC2. And this could be any orchestration engine you choose or your own Kubernetes deployment, for example. This of course means that you have the most control, but also the most responsibilities on managing things. So you need to manage the security configuration, the patching, the scaling of your orchestration, as well as your worker nodes. Then in the middle layer, what Daniel just covered is ECS and EKS. So here the container orchestration is managed for you, the control plane is managed for you, and you deploy the worker nodes in which you are running your tasks and pods in. And within those worker nodes, you of course need to manage the security, the patching, and the configuration of those nodes. And then on the top, we have AWS Fargate, where both the control plane and the worker nodes are managed for you. And basically what you do as a developer, you bring your application code, you bring your Docker files, build your container images, and deploy those in a serverless fashion on AWS managed infrastructure. And also you pay for that, the execution of those containers for the exact amount that you run them in 1 second increments.
Now that we've answered the how, we are going to be jumping into the why. So we're going to start that with jumping into microservices. We have seen containers and serverless are particularly well suited to being able to run microservices architectures. And we are seeing a shift from tightly coupled monolithic applications towards smaller independent services that that work together. This allows, in monolithic applications, what we have are tightly coupled internal services where if I do a small change, I might have a big blast radius associated with that might cause an outage of my service. Conversely, if we're looking at microservices, if I'm making changes to these smaller microservices, there's going to be smaller iterative changes as long as the front contract on those microservices is being met. The other services are not necessarily going to care whether or not we're changing the logic. So this allows us to be able to have a smaller blast radius. A good analogy on this would be Christmas lights in serial, where a monolithic application would be in serial versus parallel, which would be similar to microservice. In serial, if one light goes out, all of the lights stop working. However, in parallel, if a single light goes out, none of the other ones are going to be affected. So by having a smaller blast radius, this allows for lots of incremental change, which then allows us to be able to experiment and drive innovation at a rate of change that we as a team want to be able to move at. Having microservices also allows us to be able to scale different services up and down based upon the needs of that specific service, rather than trying to make an estimate for all of the things that are running within a monolithic architecture. Overall, looking at microservices is going to give us more flexibility while promoting better resiliency and innovation overall. There are a lot of ways to build microservices. However, there are three key patterns that work well with APIs, or specifically API-driven requests. The first is going to be the request response, in which we're going to have a specific service ask something and it's going to get some data back. We're going to have the event-driven, where I have a microservice that is looking at something or needs to be able to have a trigger happen to something else. And then I have the data streaming pattern, where I have a microservice consuming the events that are coming directly from another, or the data coming from another service. In the case of all the microservices on the screen, one of the notions that you want to be able to have is that you can see each one of these microservices has an API. The API itself is going to be the front door, and everything should be going through the front door. You should never have any side channel communication between microservices. Primarily because if everything's going through the front door, you can get an understanding of the amount of requests, you can build security. There's a number of benefits that come with this. Additionally, you want to be able to avoid breaking changes. So as long as that API is ensuring that the contract that you had set up, the backend logic about how it does that is not necessarily going to matter. The other thing on this is that you want to be able to have APIs be technologically agnostic from each other and isolated, right? So you can see in a couple of the examples that we have on here that we have a persistence layer that is abstracted away from those other microservices. Every microservice should have its own, everything that it needs to run to be able to do that, which again, that pairs very nicely with containerized infrastructure. Moving forward, as we replace some of those entries of specifically APIs and microservices, there's a number of ways that you can achieve this on AWS. And you can see on the left side here, we have mobile clients and game client that are coming into the internet, being able to be passed through CloudFront, which is our CDN, and having API Gateway as kind of the entry point into any of the services that we have in AWS. So this is generally a pretty good mapping about how that you would want to be able to build a microservices architecture within your game's backend. Moving forward, when we're looking at containers, there's also this option of serverless. So you can see that we have on the screen AWS Lambda. AWS Lambda is going to be, the serverless option here, where we're going to have a function that is going to be able to run some code and then respond back. However, not all use cases are going to be good for Lambda. And we wanted to be able to leave you with a specific flowchart that allows you to be able to make a good decision around which kind of compute you need to be able to utilize, and making a very good educated guess against that. So to start off in the top left, the deployment package size, if it's bigger than 50 megabytes, you're gonna be looking at containers. If you have a desired service that is running more than 15 minutes, I would actually argue that I would want to have it running less than 5 minutes. That would be a better containerized solution. And if I need any kind of inter-container communication or storage is storage intensive, Lambda might not be the right choice. And then from that point, I either have the option of looking at Kubernetes or ECS, as well as the targets for Fargate within them. So through this, you're going to be able to make a good educated guess around what the underlying compute resource or service you want to be able to utilize based upon the requirements of your workload.
All right, so we're going to look into a few examples. And the first one is game backend microservices. So in the first example, I have a Leaderboard microservice running on Fargate. So in the center, you can see Amazon ECS, and we are presenting a Fargate service there for the leaderboards. And within a single service, you're running one or more tasks. And typically, you would scale this service based on some metrics. So for example, the average CPU usage of the tasks might be a good metric. And you can define that you scale out and scale in based on that. So you get more tasks and less tasks based on the CPU usage. And these tasks, or all the tasks within the service, are registered to an application load balancer. So this is a managed load balancer on AWS, which integrates with ECS. And all the requests to the load balancer to a certain path will be directed to those tasks. We also have in front of the application load balancer, we have an API gateway. So this is a way for us to manage the API on a more higher level. So we can have authorization, authentication, and all kinds of additional features such as caching for the API. So technically you could host it directly with an application load balancer, but commonly you want to use an API gateway in front of your microservice. So the service uses the data storage. So this is Amazon Elasticache, and we are running an Redis cluster within Elasticache. And this is very commonly used for leaderboards. So you host a sorted set for each of the leaderboards, and this is a very effective in-memory way of storing your leaderboards. Also, when we fetch the leaderboard, we are merging that data with some data from a DynamoDB managed NoSQL database, and this would be the player data of each of those items in the leaderboard. Then, actually, if we moving forward, if we strictly follow the best practices of microservices, we shouldn't expose that player data directly to the leaderboard service, but instead we have a different microservice, the player data microservice, again running as a Fargate service, and we access all the player data through an API provided by this other microservice. And you could have both of these services registered to the same load balancer. So it could be like /leaderboards is directed to the leaderboard service, and /player data is directly to the player data service when you get those HTTPS requests into the API gateway and through that to the load balancer. So this would be an example of a microservice, and of course you could extend from there. Then moving on to another example, a bit more complex one, so hosting game servers on Fargate. So in this example, we have an ECS Fargate cluster. And within this cluster, we actually have two microservices again. So the first one is a game session placement microservice, and the other one is a scalar microservice. What the game session placement microservice does is that when requests come into the service, it will search for a free game session for the game client or the player requesting a game session. We don't do any matchmaking in this example to keep it simple. So basically, if there's any free game session, we will just provide that directly to the player. Another microservice that we have here is called a scalar. So this is a single service that has exactly one task running, but it's still, in case the task would fail, it would actually be replaced automatically by the service. So we wrap the task into a service. And what this scalar service does is that it starts new game servers per need. And the way that it figures out the need is that, again, it checks from the game server data DynamoDB table if we need more game sessions, and if there's if there's free game sessions, and if there aren't free game sessions, we will start up new ones. And when new game sessions start, they will start as a single game server tasks. So the life cycle of these tasks are basically exactly that one game session to optimize the resources. And these game sessions will then register again to the DynamoDB table to tell that I'm available for new sessions. And a feature of ECS is that you can provide an IAM role for those tasks or those services, meaning that they use that role to access the DynamoDB table in this example in a secure fashion. All right, so if we look at the whole request, we request for a new game session, goes through API gateway, goes to the load balancer, the game system placement microservice will figure out a free game session and respond back to the client with the IP and the port of that game session. And these game sessions are hosted as Fargate tasks, and they are publicly accessible over TCP and UDP for hosting this game session for us. Again, actually, what we should do, following the best practices of microservices, is that you would wrap that game server data into another microservice and access that through the API of that specific service. All right. So recapping on what we covered here. So first of all, we discussed containers, what containers are, and in the context of games, the most common use cases are game servers as well as game backend microservices. But technically, you can use containers for any compute needs that you might have, keeping in mind that maybe Lambda as a serverless option might work for some of those use cases better. One of the key benefits of using containers is that you can package your code, your dependencies, and your runtime engine and run this consistently across your local and development, test, and production environments. So you have the same image and it behaves exactly the same way on even different operating system as long as it's run as a container. And we covered our container orchestration services. So you have Elastic Container Service and you have Elastic Kubernetes Service. And these help you manage and scale your control plane without the need of managing the actual infrastructure for that yourself. And in case you don't want to manage the worker nodes either, we have AWS Fargate that actually manages the worker node infrastructure, and it integrates with both of these orchestration services. And here you actually can focus on your application logic and what matters for game. So basically, you provide your code, you provide your Dockerfile, build an image, and provide this image to AWS Fargate. We also covered microservices architecture. So the key benefits of microservices is that it decouples your application logic in small, independent, API-based building blocks, and you can easily update and replace these separately without affecting the whole system, as we discussed. All right, so some next steps that you might be interested in. So we have a bunch of resources around microservices, around containers, around game development. First one here is Introduction to Scalable Game Development Patterns on AWS. So this actually covers a lot of different use cases, but it also includes building your game backend services as REST API. So it's mapped nicely to the topics covered here. We have a blog post and a repository on improving and securing your game binaries distribution at scale. And this is actually an EKS example. So if you're interested in Kubernetes and running your game servers on Kubernetes, this example is a perfect fit for you. We have implementing microservices on AWS. So this is a general white paper covering sort of the microservices best practices and services to use to build your microservices on AWS. And then last but not least, we have the game tech landing page. So this is the place where you can find all the information you need on compute, database, analytics, and machine learning services that we provide for game developers on the AWS platform. All right, thank you. So in case you have any questions, please type them in the chat. We're here to help you out and answer any questions you have.